All right, everybody, welcome back to Diagnostic Tests. This is part 2. We'll be talking about probabilities, odds, and likelihood ratios. So before we get into likelihood ratios, let's talk about probability versus odds. If you study this elsewhere, this will be a review for you, or you can skip this little bit. If you haven't covered it much before, this will also be a brief review before we go into likelihood ratios. So what is a probability? The probability is simply the likelihood of something happening or not happening. So for example, let's say you have a bag with 10 marbles, 8 are blue and 2 are red. So what's the probability of pulling out a blue marble? So 8 divided by 10, 0.2. And what's the probability of pulling out a red marble? So 1 minus 0.8, so 0.2. And here's a little diagram of our bag with 10 marbles. So 8 blue, 2 red. So the probability of something happening can be referred to as P, and the probability of something not happening can be referred to as Q. So P plus Q equals 1. So in our marble situation, 0.8 plus 0.2 equals 1. So the probability of pulling a blue plus the probability of pulling not blue equals 1, because I said we had to pull something out of the bag, and so that's why it adds up to 1. So P plus Q equals 1. So what are the odds? The odds are a ratio of probabilities. And in terms of equation, it is P divided by 1 minus P, or P divided by Q. And in this situation, it means the probability of something happening, which is blue, divided by the probability of something not happening, not blue. So the odds of pulling a blue in our marble experiment, 0.8 divided by 0.2, 4. So the odds of pulling a blue over a red are 4. And so the odds ratio, very, very briefly in one slide, is that the ratio of the odds of something happening between 2 or more groups. So let's say now we get a second bag of marbles. 5 are blue and 5 are red. So the probability of pulling a blue in this bag number 2 is 0.5. 5 divided by 10, 0.5. What are the odds of pulling a blue in bag 2? It's 1, because 0.5 divided by 0.5 equals 1. So our odds ratio of pulling a blue from bag 1 over bag 2 is 4. So the odds of pulling a blue from bag 1 over bag 2 is 4. So let's talk about likelihood ratios now that we've covered briefly probability and odds. So a likelihood ratio is another diagnostic test property, and it's a measure of how useful or not useful a diagnostic test might be. And we can compare various tests by their likelihood ratios. And these likelihood ratios, once we get the result back from calculating them, can tell us how much more or less suspicious of a disease we should be, given a positive or a negative test. And there are two types of likelihood ratios, the likelihood ratio positive and the likelihood ratio negative. Let's talk about the likelihood ratio positive. And again, if you're like me in medical school, you kind of memorized it and fumbled through it and didn't really get it. And if you already got it, fantastic. This is a brief review for you. So likelihood ratio positive in a sentence is, what is the likelihood of having a positive test when you actually have the disease compared to the likelihood of having a positive test if you don't have the disease? In terms of the equation, which you may remember, it's equal to the sensitivity divided by 1 minus specificity. And so the numerator, being the sensitivity, is the true positive rate, which we covered in the previous video. And the denominator, being the 1 minus specificity, is the false positive rate. And here's the slide from the previous video as a review if you'd like, for the false positive rate. So all these 10 subjects do not have a disease. If the test is 60% specific, it'll call 6 out of the 10 as true negatives and misclassify 4 out of the 10 as false positives. And so we have 40% false positive rate. So likelihood ratio positive is sensitivity divided by 1 minus specificity. Again, sensitivity divided by 1 minus specificity, or in even simpler terms, it's the true positive rate divided by the false positive rate. I like to call it's the hits divided by the false alarms. Now, to have confidence in a positive test that is a true positive, you want a really big likelihood ratio positive. So an excellent likelihood ratio positive is 10 or above. So if you have an LR positive of 10, it means you're 10 times more likely to have a positive test with the disease as opposed to having a positive test without the disease. A very good likelihood ratio positive is 6, fair is 2, and useless is 1, because if it's 1, it means your true positive rate is equal to your false positive rate. So you want a very big likelihood ratio positive to make you feel more confident about a positive test. So in a bit of a graphic here, if you have a patient you're seeing and you run a test, them, it comes back positive, and that's you, and you want to make a diagnosis. If a test has a very large likelihood ratio positive, you take a big step towards a diagnosis. If it has a likelihood ratio positive of 1, you stay where you are, because the true positive rate is equal to false positive rate, and you're no further ahead. And if the test has a likelihood ratio positive that's less than 1, maybe just think about backing away from the diagnosis, because it may be more of a false positive. So let's now talk about the likelihood ratio negative. So it is, what is the likelihood of having a negative test if you have the disease compared to having a negative test without the disease? And the equation is 1 minus sensitivity divided by specificity. So our numerator is the 1 minus sensitivity term, and we saw that in the last video, which is the false negative rate. And the denominator is specificity, which is the true negative rate. And here's a slide from last time. All these 10 subjects do have a disease. And this test, for example, is 70% sensitive, so it picked up 7 out of 10 as truly having it. But it said 3 out of 10 did not have it. And so that's a false negative rate. So the equation, 1 minus sensitivity divided by specificity, or to simplify things, the false negative rate divided by the true negative rate. So if you can remember these terms, false negative rate, true negative rate, and what it means, you can figure out if it's 1 minus sensitivity or whatever else, in case you can't remember. So this time around, for likelihood ratio negative, we want a very small likelihood ratio negative. We don't want many false negatives. So an excellent likelihood ratio negative is 0.1 or smaller. Pretty good is 0.2, fair is 0.5, and useless, as you can imagine, is 1, when your false negative rate is equal to your true negative rate. So same patient, you run a test, it comes back negative. That's you. You don't want to make the diagnosis depending on the likelihood ratio negative. So if it has a small likelihood ratio negative, take a big step away from the diagnosis. If it has a likelihood ratio negative of 1, and I apologize, a typo there, stay where you are. And if it has a likelihood ratio negative, apologies, that's greater than 1, maybe the patient actually has the diagnosis. So let's go back to our hockey hair study. What's likelihood ratio positive and what's likelihood ratio negative? So here's our sensitivity and specificity, hasn't changed. Likelihood ratio positive is sensitivity divided by 1 minus specificity, which is the true positive rate divided by the false positive rate, equals to 0.3 divided by 1 minus 0.25, and the likelihood ratio positive is 1.1. So this test is pretty much useless, and we kind of saw this in the positive predictive value, how low it was. But it's even worse now because you're pretty much as likely to be called a hockey star compared to when you're not. So not very helpful. Likelihood ratio negative is 1 minus sensitivity divided by specificity, which is the false negative rate divided by the true negative rate, which is 1 minus 0.83 divided by 0.25, which is 0.68. So it's a little worse than fair, but also getting close to 1. So it looks like our test isn't very good, and it kind of sucks, unfortunately. Something that's important to remember about likelihood ratios, as opposed to predictive values, the likelihood ratios should not be affected by prevalence in your population. Because the likelihood ratios are derived from sensitivity and specificity, which we said in the last video are not affected by prevalence or shouldn't be, it follows that the likelihood ratios should not be affected by prevalence. So that's why we feel a bit better about using likelihood ratios. It gives you a bit more information than the predictive values. But unfortunately, our test still kind of sucks. So they're more stable than a negative predictive value and positive predictive values. So we have all these numbers back: sensitivity, specificity, positive predictive value, negative predictive value, likelihood ratios. But what do we do about them now? How does it affect our decision making? So you get a test result back and it's positive. Do we actually think the patient has a condition or not? So if you know the prevalence of a condition in your population, that becomes your pretest probability. For example, if you're working somewhere with more older people and people come with chest pain, you'd expect prevalence of coronary artery disease causing myocardial infarction to be higher than if you work in a pediatric emerge where you don't expect children to be having ST elevation myocardial infarctions because of atherosclerosis, for example. But in general, though, we don't really know the true prevalence of a condition in our population. We don't necessarily know what percent of your population might have CAD, for example. So we use our history and our physical and our knowledge of the community and the patient population we work in to estimate a pretest probability. So let's take our hockey hair study. So let's pretend that a player who used to play for a farm team shows up and want to play for our team for some reason. And you think they're actually pretty good, and you think, you know what, maybe their pretest probability of being a hockey star is 90%. They played in farm teams. This is better than most of the folks who've showed up to recruiting. So what's their post-test probability if we run the hair sample test on them? A couple ways you can do this. You can use Bayes' theorem, which is your post-test odds equal your pre-test odds times the likelihood ratio. And as we saw earlier, odds and probabilities aren't the same thing, but we can convert between them. Most of us, though, tend to like to think in probabilities more than odds, for example. But if you want to go down the odds routes, you convert your pretest probability to odds using this equation here. You calculate likelihood ratio positive, or you know that already. Calculate Bayes' theorem, so you plug in the numbers. And then you convert your post-test odds of probability using this equation, and then you get your post-test probability. So for example, 0.5, or sorry, 0.45, apologies. Or something much easier to use is the Fagan nomogram that allows us to think in probabilities. And so you have to determine what you think your pretest probability is depending on your knowledge of your patient and population. And then you take a straight edge of any sort and you draw a line from your pretest probability, which is 90%, through what your likelihood ratio positive is, in this situation, 1.2, and it spits out your post-test probability, which is still 90%. And we already knew our test wasn't very helpful, so our test didn't really help us feel any much better if our new recruit is a hockey star or not. It's the same thing we thought, unfortunately. Well, let's say I show up for hockey practice and real talk, I have zero hockey skills at all. I'm going to peg my pretest probability at being somewhere up here, but unfortunately the nomogram starts here. Likelihood ratio negative is 0.68, and I'm trying to line it up. My post-test probability, also off the charts, terrible. So unfortunately this test also didn't help all that much to make me feel a bit better about maybe being a hockey star. I still know that I'm not. And so maybe if I join the team, I'll get a medal for participating or something, but still not a hockey star, and that's okay. So summarizing part 2, probability is the likelihood of something happening or not happening, which is P plus Q. Odds are a ratio of probabilities, P divided by Q. The odds ratio compares the odds of something happening between 2 or more groups. A likelihood ratio is another measure of how useful or not useful a diagnostic test is. And it lets you judge the significance of what a positive or negative test means. Do you feel more confident about making a diagnosis, or more confident about not making a diagnosis, or not all that helpful? And the Fagan nomogram helps us to think in pre- and post-test probabilities and incorporate likelihood ratio to adjust our suspicion of disease up or down.